First, I would like to thank the organizers for putting this workshop together. As we saw yesterday in the opening remarks, we still have a lot to do in terms of diversity for the main machine learning conference, and I think this workshop is a very good step towards that. Just to correct a bit about my background, I think that bio is a bit outdated. That was true up to 2016, but right now I'm a research scientist at DeepMind since 2016. But I'll also share a bit of my personal background, so this will be clear throughout the talk. So I was asked to actually talk a bit of my personal background, and I decided to do this talk like just interleaving everything, like my personal background, my technical background, and also my research interests. So the talk will have like different blocks. So since we have a smaller audience, maybe we can take advantage of that. And if you have like questions, and you can interrupt and ask, and then I'll skip if necessary in the interest of time, but feel free to ask questions in the middle, because towards the end it might be too old news. So the outline goes more or less like this. I'll start talking about pointer networks. That is work that I did while I was a PhD student in Berkeley, a math PhD student. It covers like geometry, so using deep networks to try to solve geometry problems. It also covers RNN architectures and memory augmented networks. Then in 2016, I joined DeepMind, and my first work there, it was called like Bayesian recurrent neural net, so I'll refresh a little bit about that. And again, this is kind of connected to pointer networks in the sense that it's about RNN architectures, but it brings like parameter uncertainty. So you have like a Bayesian view to this thing. In 2017, after being a while at DeepMind, of course, like you start getting a bit of the RL emphasis because DeepMind is very RL based. So I decided to try a bit of these ideas from the Bayesian recurrent neural networks and to bring this parameter uncertainty now to RL and see where we can get that. So I'll talk about this work as well. And then finally, I'm going to connect the dots and arrive to the now, where I've been working on like in a memory task suite, where the goal is to understand the role of memory in agents and in tasks. And hopefully this outline kind of shows more or less how the journey happened from a math PhD to being in deep learning. But I'll share more as we go through the talk. So let's start with like pointer networks, okay? So this was work presented back in 2015 in NeurIPS. It was joint work with Oriol Vinyals and Navdeep Jaitley. At the time, they were at Google Brain, so I was at UC Berkeley, so the collaboration was easy. And the question we were interested in was, can neural networks learn basic geometry? So let's say you have like a set of points, and you want to compute the convex hull. So the convex hull is the smallest convex set that contains these points, right? So you can determine this set by just telling what are the connections of the points on the boundary, right? So if you have points P1 to P10, you can say, well, the convex hull is the sequence that joins points, let's say, here P2 to P7, P6, and so forth. So you can describe that as a sequence, okay? So in the same gamma of problems, you can think about like Delaunay triangulations. What are these? Given a set of points, you want to find a triangulation. So the elements are triangles and they don't overlap. And each of these triangles is Delaunay. What does that mean? When you draw the circle that contains this triangle, no other points from the initial set of points is inside this circle. So if all your triangles are Delaunay, then your triangulation is Delaunay. Also, we looked into the traveler salesman's problem. This is a known problem because NP-hard, many people are interested. For example, like the post office and other companies would be interested in solving this problem for sure, where you have a set of points and you want to determine the shortest path that passes through all these points, okay? Once and only once. So these were the problems we were interested at, and how did this interest come about? So again, I will interleave like technical and personal stuff. So my background, I'm Brazilian. I'm born in this very small city in Paraná, in the south of Brazil. There what it is. It's close to the border with Paraguay and Argentina. Let's see. I went for my undergrad and my master's at Unicamp in São Paulo. I was studying pure math, so I was studying theoretical partial differential equations. And then in 2010, I went to UC Berkeley, where I was using partial differential equations to generate meshes. There will be more about this later. So in the meanwhile, in 2015, I had this paper that was pointer networks that I find that kind of the milestone that determines my change from math to machine learning. So it was when I started, and in 2016, I joined DeepMind, and that's where I am to the present. So let's talk about this was my thesis title, is like high order unstructured curved mesh generation using the Wieslow equation. It's very long, but it's very descriptive, and I'll go like turn by turn and stop me. So let's see what was this about, okay? So first, a mesh. What is a mesh? Mesh is just like discretization of a domain. You can think like in 2D, it can be triangulations, or it can be Cartesian grids, or you can have things that are called like boundary layers, or you can have 3D things with tetrahedral or other shapes of elements, okay? So you need these meshes because if you want to solve equations on these domains, the first thing you need is a good discretization, and the quality of discretization correlates with the quality of your solutions. So let's say you have a mesh that's a triangulation, so the elements of this mesh are triangles. So what you do generally, you track what happens at the vertices of this mesh, and then you tell what's the connectivity between them. So if you have a normal mesh, let's say like a linear mesh that they are called, this is what you have. You track what happens at these vertices. But now if you have a higher order mesh, you also start having points that go across the edges and also inside the elements. And you're interested in both the position of these points and what happens to functions at these points. So this is the high order part. Now what's unstructured means? So unstructured, it basically connects to the connectivity of your elements. So if the connectivity is constant, you call it structure, so you can see here to the left. And if the connectivity varies, it's unstructured, so it's only that. Now, curved. So curved means that your elements are not necessarily just straight-sided, they can also be curved. So here we have like a curved edge, and here for 3D elements, maybe you can see that these things are curved. Okay, and now how about using Wieslow equations? So the Wieslow equations, they're just like partial differential equations. They come from the Laplace class. And the idea is that to generate a curved mesh, what you generally do is you can generate very good straight-sided mesh through handwritten rules. So there's software that you can generate these automatically. So what you do is you start from these straight-sided meshes, and you call this your computational space. So you're going to write these equations, they are the Wieslow equations, here in this computational space. And then you're going to match the boundary conditions for the curved space. You know the boundary conditions because that's the domain that's specified. And then to determine the position of the other mesh nodes that you're trying to generate, you just solve this PDE for the interiors. So you put Dirichlet conditions on the boundary, and you solve for the interior points. So that's what happened. So this is for my thesis. We are generating these cool meshes, but then I started getting into deep learning, reading, doing Coursera courses, and I was like, well, instead of using generating high order unstructured curved mesh using the Wieslow equations, of course, what I wanted to do is, yeah.
Can I ask, what does the Wieslow equation relate to? So why that PDE and not another one?
So this is, so they are Laplace, from the family of the Laplace equations. So they spread the nodes like quite nicely, and they minimize energy. And they also have some theoretical guarantees that you will, because when you match the boundary conditions, you have the elements that start tangling. Let's say if you have a boundary layer close to your curve conditions and you match there, then you get all tangled. And the Laplace has special conditions that will, in theory, untangle these for certain domains. Yeah. So we wanted to do this using deep learning, right? But I was far along in my PhD. This was 2015. I was finishing in 2016. So Of course, I could not just try to solve the whole problem, so I started like simplifying as much as we could. And we said, okay, so instead of trying these super complicated meshes, let's just do like Delaunay triangulations using deep learning, because that seemed like possible to do. And Delaunay triangulations are very special for the meshing community, because in 2D, for example, they have this property that they maximize the minimal angle in the triangle, so your solutions are going to be more accurate. So it had a cool connection, so it seemed like worth a try. So, okay, just like reframing pointer networks. The goal was like to try to model these mappings where the outputs are subsets of the inputs. So for example, in the convex hull here, you can see your inputs is a set of points that goes from 1 to 6. And then the convex hull, you can determine these as these like 2, 6, 5, 3, 2 sequence. Then we have the TSP at the same time, the same way, and the Delaunay triangulations where you're trying to determine the connectivity between the points. So our first attempt back then, it was just to apply vanilla sequence to this problem. So you input the 2D coordinates of your points, and then you just output this sequence representation of the convex hull one at a time in an autoregressive fashion. But this has limitations. First, at decoding time, so here, when you're at the purple stage, when you're trying to predict your output, you don't look back at the input sequence. So that's like, this model lacks memory. So it relies a lot on everything that's in this last state of your input sequence. And also, the fact that you have like a softmax over a fixed dictionary, so here your dictionary is the number of elements of your input sequence, it doesn't allow you to generalize for longer input sequences. Because so let's say you train your models up to 20 points. Now if you have a set of 21 points, so you have this character that is like the number 21 that you have never seen at training, so there's no way to assign probability to this new token. So then one way to get around this is to augment this model with attention. Nowadays, attention models are super popular, but back then they were just starting, so now we have the transformer. We know that these memory-augmented things are super powerful, and they paid off. So, of course, we also tried it at the time, and it got rid of this limitation that I said, because now it was memory-augmented, but it still have this problem of having a softmax over a fixed dictionary. So the results were better, but still not good. So we submitted, I think up to here, we submitted this paper to ICML 2015, and it was rejected. Then we started like kind of shuffling ideas around, and pointer networks came about. And the idea is, at decoding time here, instead of setting probabilities over a fixed dictionary, we were setting your output to be directly already the probabilities, the weight for the attention that you had over the input dictionary. So everything that is in your input sequence has a probability assigned to it, so it close to the set of problems we are looking quite nicely. So it got away from the limitations that we had, and it had very nice results at the time, and it was also like introducing kind of like a new set of problems that people were thinking about how to solve with neural networks. There was like some interesting follow-up work. There's lots, because this is work from 2015, but I decided to point out this, that is Pointer Sentinel, for example, from people from Meire et al. That was an effective way of rendering rare or unseen words in language modeling. So you can kind of like switch from the normal classification problem that you have in general modeling to using the current context that you have, and then you can assign probability to unseen or rare words in a more meaningful way. There was also matching networks that wield improvements in one-shot learning for ImageNet. And most recently, I don't know if you heard about this agent that is called AlphaStar. That's an agent for playing real-time strategy games. That's called StarCraft 2. It was able to beat a professional players in the full game of StarCraft, but the AlphaStar architecture is super complicated, so there are many like ResNets and LSTMs and many complicated things, and one of the complicated things it has is a pointer network. So what is the pointer network doing there? So the game has like several units, and you have to decide what you do with the units. So you have to cast actions there. And it's impossible to track all the actions for all the units. So what you do, you're going to select a subset of these units that you're going to cast actions. And you use a pointer network. So the pointer network architecture is perfect for that. If you want to select a subset of your input that you want to decide to do things. So now perhaps in the interest of time, I will skip this session. But this was just like, instead of training a neural network with deterministic ways, you replace that for a probabilistic distribution, and you do this in a variational fashion, like Aji was telling before. So you use the variational approach, and you have richer representation and principal regularization. Now, let's talk about like noisy networks for exploration. That again has the same idea of, instead of having deterministic weights, you have probability distribution. So there is noise associated to that. Every time you sample, you get different weights from your network, but that is now in the RL framework. So the idea was that you're going to replace your exploration scheme by this noise. So let's say in DQN, instead of have epsilon greedy, now you have these noisy weights that every time they give you different behavior in the policy, or instead of having this entropy cost for A3C, now you have the weights, the noise on the weights. And you learn this noise through backpropagation. So this was work done in collaboration with Mohammad Azhar and Bilal Piot back in 2017. And at the time, we were seeing like very good improvements over the whole Atari suite. So if you looked at overall performance for both A3C and DQN, noisy nets were yielding better results. Most importantly, and I think more revealing, was this follow-up work done by Hassel et al., so and colleagues at DeepMind, that it was like combining the improvements in deep reinforcement learning. So basically, they took like several like recent papers in reinforcement learning that had all orthogonal techniques, so double DQN, prioritized replay, dueling networks, noisy networks, and they started to analyze how do these methods or techniques combine together. So it ended up that the combination of all of them at the time provided state-of-the-art performance on Atari, both in terms of data efficiency and final performance. And here you have a graphic where you can see how it was. So here are all the other baselines, and this is the rainbow baselines that they call. That is all the techniques all together. So it was like a very cool result to see. Because like many times you write a paper and you say, oh, this is orthogonal to this idea, but you actually never get the time to test everything, to do the proper ablation. So this was a very cool like ablation paper. Finally, we arrived to the now, and I'll talk about like this memory task suite that I've been working on in collaboration with Melissa Tan, Brian Faulkner, and Steve Hansen, and many others from DeepMind. It's a very long project. It has been going on for more than 1 year, and we are hoping to submit it to NIPS. So this is still like kind of not completely finished work. And let's see. So the goals of this work was to ensemble a set of memory tasks and do training test splits in a way that we are going to test for generalization. And besides that, we are going to introduce a new agent architecture, and this agent is going to have like an external memory, so like DNC style, but a bit simplified with key and values structure. And we'll compare this baseline to other baselines and do many ablations. So for example, if you have this baseline and you add some auxiliary loss, how does it perform? Or like with different auxiliary losses. And instead of looking at performance or just like training as we do in RL, we look at this test performance and like the generalization gap, let's say. We are very interested in that. And also overall performance, how each baseline is doing across all the tasks and not just like a single task. And the tasks, some of them were already designed and some we design ourselves that they're supposed to test for memory. So I'll talk about some of the new tasks. These are archetypes. They're probably going to be open source later together with the paper, but for now I'm just showing a sketch of how they look. So we have this class that's called like spot the difference. The idea, there are 4 different tasks for this, but the general idea is that you have an agent that spawns in this room, and he has to look around, and later this agent is going to navigate to the room B, where everything is the same from the first room, except one thing that has changed, and the agent has to identify what has changed. In this case, it's the color of this object, but it could be more difficult things. For example, these objects might be moving, and here they are moving like this and like this, and maybe here this one is moving as a circle, so that is the difference. The object looks the same, but the pattern of the object is different. Then we have like navigation tasks, where the agent is in a maze, and he has to locate a goal. And then he has a fixed amount of time in this maze, and every time he finds the goal, it respawns again in a different location and has a second opportunity to find the goal. So if the agent is able to remember the map setting and the goal location, it's going to find it faster and is going to maximize the reward because it can go directly to the goal. But it needs to have very good memory for both navigations, and also it needs to memorize where the goal is. We also look at like transitive inference tasks. So we want to measure the ability of agents to understand ordering of elements in a transitive fashion. So let's say you have these elements here on the top that they are ordering. This is the smallest one, and this is the largest. So they are ordered like this. The task is like at training time, the agent is presented with these 2 objects. If it picks the biggest of the elements, in this case the blue one, because here is the order, then it gets a reward. If it doesn't, then it respawns again, and it can choose to pick again, and then it keeps respawning until it picks the right one. This is doing training. Not at test time, what we do is we present pairs. So at training, we present all the consecutive pairs, and then at test, you start putting a distance between the pairs that are presented, and the agent has to infer this transitive relation that there is in the ordering. So here it sees the blue and the orange, and it has to figure out that the blue is the biggest one. Why? Because it has seen that it's bigger than the yellow, and that's bigger than the orange, so the relation goes that way. And the position of the objects here, they do not relate to the order there. So you change things, so you're really testing for the memory of the agent of remembering the color association with the ordering. Okay, so this is like doing training, but now how about tests? So the idea of like the training test splits, it was to test for 2 different things. There is something that we call scale. So for the spot the difference, you can think of like, so here we also lock the agent a bit in this corridor so that you make it harder for backpropagation methods to work. So you can think the scale of being the duration of this delay, or maybe the number of objects that you have in the room, or the size of your map here, or the length of the chain in this transitive inference. So during training, we're going to vary this scale. So we're going to vary the number of objects, we're going to vary the map size, we're gonna vary the length of the chain. But now during test, we're gonna test in different scale. So we have 2 modes, one that's interpolate. So that is, let's say that during training you see things in scale, let's say you see it small and large. So at test time, you see median scale. So it's a new scale, it's unseen, and you have to see if you generalize. But we also test for extrapolate mode, so bigger scale. So you say extra large scale, and you see how your agents do that. And we also test in terms of stimuli. So things like colors and motion patterns here in the spot, the difference at test time, they're always going to be unique. Or the texture of your objects, or the layout of your maze, or the position of the buildings, or here where the agent is spamming, is going to spam in brand new locations, so it has never started from there. It has to understand how is the maze positioned. And then for the transitive inference, is the length of the chain and the color. Okay, so we also have tasks in this PsychLab suite that's neuroscience inspired. So many of these experiments, they were heavily tried in neuroscience, and they test for very specific types of memories in humans. So then you put them in agent, and you try to see if the agents also have this sort of performance. So one of the tasks is kind of this arbitrary visual mapping, where you have, so first you see an image. Let's say the first time you see an image, it has a direction associated to it. That's this green point here. It's saying, wow, this is the right direction. Then you're gonna see many other images, and later in time, you're going to be presented with this image again, but now you don't have a direction associated anymore. It's like all black, and you just have to remember. So you have to associate each image with a direction. This is called like a free recall task, because you only need one moment back in time to remember, but that one is very key. So if you don't remember the first time you saw this image, you can be at least at most a chance at this time. So this is testing for something that's called episodic memory. And we have other types of tasks, like for example, this one, that's what then where, that you see an MNIST digit first, and then later you have to find it here and find the direction associated to it, and others. So it's just an overview of the tasks. And then for the memory agent, the new architecture that I said we are introducing. So basically, as I said, it's a way of integrating an episodic memory. So here, external memory, you write and read from at every time step. In a working memory, that you can think of an LSTM, or maybe even like a feed-forward network, just your controller. And how does this thing interact together? And then we also studied the role of adding auxiliary unsupervised losses here to this controller. So let's say you can have a reconstruction loss coming out of this model here from the input, or you can have like a CPC, so contrastive predictive coding. That's a way of trying to predict future steps given your current observation. We have like, I think a set of almost 20 tasks and maybe 10 different baselines, so it's a lot to talk here, but I'll give you like the takeaway so far, is that for the most tasks, there is a gap in performance when comparing training tests, as kind of expected, but you never know. In RL, maybe it would be perfect, right? In some tasks, it is perfect, but most tasks, there is this gap in performance. And for the extrapolate mode, so modes where the scale is bigger than what you see in training, is even worse. And then there is like some of these free recall tasks. For example, this one that I talk about, the AVM, where you have to remember the associated direction for that. Like models like LSTM, they don't do very well in this task. You really need to have an external memory, because there is like one point back in time that you need to recall the information, and then LSTMs, maybe like they remember more like the general sense than one particular step time. So this type of task, it's proof that you need kind of an external memory to do well. Another surprising thing was that a feed-forward controller can do surprisingly well in many tasks. It's funny how like nowadays no one ever tried like feed-forward baselines, but they're decent. And the unsupervised losses generally help performance. So if you have an LSTM and you add, let's say, even a reconstruction loss, that's probably helping you with having better representations. So in general, you also do better in the task. Yeah.
Does the representation itself change through time as you change the model, or does it stay kind of as the unsupervised representation?
Yeah, we have not looked at this specific ablation. Yeah, it's just like more in terms of like performance, but not exactly like if the representation is changing. Yeah.
I just want to know if like you can learn it sort of task dependently, or you have to get it right from the kind of supervised curriculum.
Yeah, that's an interesting question. Yeah. Okay, that's very well timed, because like now I'm going to change gears and talking about something not technical. So if you have questions about the technical part? Maybe it's a good stopping point? Yes. Yeah. Yeah, I think so. It looks like it. Okay. Great question, Jose.
Yeah, so going back to the pointer network,
Yeah.
I was wondering, the solution is invariant to starting point.
Oh, yeah. So we fix, so that's a very good question. So indeed, there are no unique solutions like for the convex hull, right? If you cycle through the convex row, not only through the first point, but also like through the directions. So we chose an ordering and we made sure that it was unique. So we always made it the first element to be the smallest one, and we always chose like counterclockwise direction. And then for the Delaunay triangulation, we also chose like the triangle that had, so we ordered the circles of the triangle, and we took that ordering. So yeah, otherwise you have several modes, and then just doing classification is not very easy. Yeah, very good question. Okay, so back to the cat. So the cat now is work too much. So I want to talk about Khipu, that is the Latin American meeting in artificial intelligence that I'm a co-organizer. We also have other two co-organizers here. Martin, raise your hand, like there. And Jose, raise your hand. Yes, there is Jose. So you can talk about it to either Martin, Jose, or myself. So what is Khipu? Khipu will be a 5-day conference in Montevideo, Uruguay, and will be focused in artificial intelligence and more specifically in machine learning. We're gonna have like very advanced training workshops in a summer school style, so lectures that will have coding sessions paired with it. But we also have research talks, so if you're an advanced researcher, you're also welcome to apply. There'll be space for presenting your work, talking about it. There'll be like selected spotlight talks where you're gonna have time to share your work with other people, and also networking events, so lunches, gatherings, etc. So why this name, Khipu? So Khipu were devices that were made from strings, and they are basically recording devices that were used from a number of cultures in the region of the Andean South America. And they were similar to abacus, so they were useful for collecting data, keeping record, monitoring tax obligations, etc. So we already heard a bit in the opening remarks yesterday about the lack of like country representations here at ICLR specifically from people coming from Latin America and Africa. And this is a blog post, this is taken from a blog post that was calling The Missing Continents, that shows the countries rescaled in proportion to their accepted papers at NeurIPS from 2006 to 2016. And you can see that we have like very underrepresented both Africa and Latin America. But things have improved a lot since 2016. So in 2017, we started having this like deep learning in Daba. That's a machine learning conference that happens in Africa every year. They rotate the country, and it's like super nice. And after that, actually the next year at NeurIPS, there were like 3 papers that were submitted from the authors that were Africans and still in African institutions. And our idea is to do a similar event for Latin America, and this is Khipu. So Indaba is really an inspiration for us. Here I'm showing some statistics from Indaba. So you can see like the growth in attendance. So back in 2017, they had 300 attendants, and now in 2019, they have 1,000. Then the women participation also is improving. So they started from 70 out of 310. So even back then, it was already better than what we have here at ICLR. But the next year, 2018, it was also better, and also the representation per country. So we want also to achieve similar diversity topics, for example, in terms of country representation from Latin America, gender representation, institution representation, background representation. So we want to have students, researchers from academia, researchers from industry, and coming from all countries. So we are lucky to have a very prominent set of confirmed speakers. I'll leave you some moment to look at the faces or read the names. You might recognize some. For example, we have here Joshua Benjo and Jeff Dean, Oriol Vinyals that is here in the room, but also like Chelsea, Luciana Ferrer, that's in University of Buenos Aires. And our target is to have 350 attendees coming, as I said, from academia and industry, both students, postdocs, researchers. The application is free, the registration is free for students, sorry. So the selected students will have free application, free registration, and you can also apply for travel and accommodation scholarships. And the applications are open. So if you're interested in this event, please apply, come to talk to me, Martin, Jose. And also we have like a webpage with more information, is Khipu.ai. And we also have a Twitter account that we try to post updates on this event. So please feel free to take a picture of this slide and talk to us, and we are happy to answer questions.